Hello, good evening. Welcome to this week's live session number 6. So, in today's session, we will be discussing about the vibration analysis of 2 degree of freedom systems. So, till now, we were discussing about vibrations of single degree of freedom systems, and in this week's lectures, we have seen how uh, basically how to write the equation of motion, how to derive the equation of motion for systems with multiple degrees of freedom, which basically includes like the simplest multi-degree of freedom system is a 2 degree of freedom system. So we will go through the derivation of the equation of motion for one familiar system, which is basically we will try to model a car. So we will basically go look at the what is called as what is popularly known as the quarter car model. So it is modeled as a 2 degree of freedom system. So we basically model the car body along with all the passengers and as a one lumped mass. Then we model the tires and basically the wheels basically together as another mass, and we model basically the stiffness and damping of the suspension and the stiffness and damping of the tires. So in today's session, we will basically go through how to derive the equation of motion for this quarter car model. So in this model, we say that the car is modeled as this upper mass, let us say m1, and we have a spring, let us say k1, and a damper c1. So this k1 and c1 basically represent the suspension, this is basically the car body. Then the mass m2 represents the wheels, and we consider another set of spring and damper, basically k2 and c2, which represent basically the stiffness and damping of the wheels and tires basically. And so the wheel can be represented something like this. So when the wheel moves over the road, because of the suspension, the wheels move up and down, and there are some forces basically and some vibrations which are transferred to the car body. So ideally the function of the suspension would be so as to transfer as less vibrations as possible to the car body and the passenger, so as to ensure comfort of the passengers. So let us say if the wheels go over some bump or in something or some obstruction, then whatever let us say excitation which let us say we call E of t, let us say that is the excitation or that is basically the displacement of the wheels. So that irrespective of whatever displacement excitation et, we would want the, so let us say we call the displacement of the mass m1 or basically the car body with respect to its equilibrium position as y1, and the displacement uh, of the mass m2, let us say we designate it as y2, and here the displacement of the v, we are writing it as e of t. So for this kind of a system, we would want the displacement y1 should be minimum, or we would want the car body to move as less as possible, irrespective of whether the wheel is going over some bump or some speed breaker or anything like that. So that is the function of the suspension. So now here this is popularly known as, in literature it is known as quarter car model, and so here in this session we will try to derive its equation of motion, and then we will try to solve this equation of motion using basically the simple approach. We will extend the same approach as single degree of freedom system, and we will try to solve the same differential equation, set of differential equations. Now here, because there are two masses, so there are 2 degrees of freedom, so we will have a set of 2 differential equations because it's a 2 degree of freedom system. So we need 2 coordinates y1 and y2 to basically describe the behavior of this system completely. So let us start with the derivation of the equation of motion. So for that, first we will have to draw the free body diagram of the masses m1 and m2. So let us say if we first start with the mass m1. So let's first draw the free body diagram of mass m1. So it is connected to mass m2 through a spring, and the spring force acting on this mass will be basically because of the difference in the coordinates y1 and y2. So it will basically be k1, let us say k1 into y1 minus y2, and similarly the force due to the damper will be proportional to the relative velocity between the two masses. So it will be basically c1 into y1 dot minus y2 dot, and similarly let us draw the free body diagram for the mass m2. Now we have the same forces because they are both connected together by the same spring, so we will have the same force acting upwards. So let us say we have the coordinate system such that upwards is positive, so we will have the same forces and here on the lower side of the mass, so we will have the force due to the other spring. So let us say it is proportional to k2 into the difference between the basically the difference between the tires will basically get will be moving up and down. So the mass m2 and will be moving up and down, and also the wheel is moving up and down. So there is a difference y2 between y2 and e. So that is will cause the compression and of the tire. So when it moves over the compression, and again it will get released when it goes over uh, so the tire also goes through like gets deformed and keeps expanding and contracting depending on the condition. So this is basically the free body diagram of the other mass. So here we are assuming that y1 and y2 are measured with respect to the equilibrium position. So this is important because then that will so then we can actually safely neglect the weight of the masses m1 and m2. That will not they will not contribute as a dynamic force in the equation of motion. So basically the static deflection basically the force due to the static deflections that will balance the weight, and when basically the displacement is measured with respect to the equilibrium position, then we will not get the weight in the equation of motion. So let us try to write down the Newton's second law for the masses m1 and m2. So since the force, there are these two the spring force and the damper force that are acting on the mass m1, so then we will write, so m1 y1 double dot will be minus, because the forces are downward, and similarly for the other mass m2 y2 double dot will be, so there will be these same forces k1 y1 minus y2, so c1 y1 dot minus y2 dot minus k2 y2 minus e minus c2 y2 dot minus e dot. So so then basically we get these two equations of motion, and so then we can write these equations of motion in a matrix form, so that will basically help us in collecting all the terms together, and then we can write the equation of motion in the matrix form, and the form of the equation of motion will look similar to the single degree of degree of freedom kind of a equation of motion. So let us say we form a mass matrix, let's say M1, 0. So that will basically help us in writing these equation of motions in a more compact form. and then we will have the stiffness matrix. So we can basically collect the stiffness, the basically the all the terms which contain y1, y2 and its derivatives on the left hand side, and on the right hand side we will collect the other terms which basically indicate the forcing terms on the system. So on the right hand side we have basically the terms which are coming into the differential equation because of the presence of the bumps, basically the wheel is contact with the road and the road profile is uneven, so that is why there is a change in the value of E and its derivatives, so that will cause a force being transmitted from the road to the wheels and then from the wheels to the car body through the suspension and damper. So this is like basically the spring and damper of the suspension. So this is basically the equation of motion. So this particular matrix is called the mass matrix. This is basically the damping matrix, and this is basically the stiffness characteristic of the system. And the terms on the right hand side are basically the external forcing. So the system is subjected to some forced vibrations because of being in contact with the road. So the road profile causes some displacement of the wheels. The displacement of the wheels causes deformation of or basically the road bumps cause some deformation of the tires, and because of its stiffness and damping characteristics it transfers some force through the suspension from the wheels to the car body. And so we will basically try to study how the stiffness and damping characteristics of the wheels and suspension, how do they impact the response of the to a certain set of forcing conditions or road bumps. First we will try to study the free vibrations response, and then we will later on look at the forced response because of the presence of the road. So let us derive we have derived the equation of motion. So let us say we call the mass matrix as capital M, the damping matrix as capital C, and the stiffness matrix as capital K, and the right hand side forcing terms as F. So we can write basically the equation in this form. So let us denote the mass, stiffness, damping and stiffness characteristics as like capital M, C as for damping and K for stiffness, and we will write the vector basically Z. So we will write the vector of y1 and y2, we will call it as Z. and z double dot is, or z dot, let us say for is, will be y1 dot, y2 dot, and similarly z double dot will be the vector y2 double dot, y1 double dot, and y2 double dot. So this is the uh, notation that we are using for this particular problem. So this is the general form of the equation of motion for any multi-degree of freedom system. So we will have a mass matrix, stiffness matrix, and damping matrix, and we will have the derivatives of the uh, vector which contains the displacements of the individual masses, or basically the coordinates y1 and y2 and its derivatives. So let us say we have the solution of the form zt. So we assume, let us say there is a solution of the form lambda t. For the homogeneous differential equation. So let us say we call it as ZH, solution to the homogeneous differential equation. Or basically what we generally call it as complementary function. So that will be basically the response to the homogeneous differential equation. So we basically the total solution will have two parts. Will be have the solution to the homogeneous differential equation and plus zp of t, which is basically the particular solution. So the first part of the solution is basically the solution to the homogeneous differential equation. So we will that is basically the represents the free vibration response of the system to and that depends on basically like the stiffness and mass, like the mass and stiffness characteristics of the system. So we will first try to derive that. So when we substitute this solution in the homogeneous differential equation, we will get so when we substitute this homogeneous solution into the differential equation, we will get this equation of the differential equation will become like this. So we have m lambda square plus c lambda plus k, this whole matrix into v e to the power lambda t is 0. So this is basically uh, not equal to 0 for any real value of time. So and the right hand side is 0. So basically uh, this equation will have a non-trivial solution when the determinant of the the determinant of m lambda square so when this will be 0 for non-trivial solution. So for V to be a non-trivial solution, we need to have the determinant of m lambda square plus c lambda plus k is equal to 0. So basically when we multiply the mass matrix by lambda square, then the damping matrix by lambda, and the stiffness matrix, that if we combine together and add that, so we will get this as our characteristic equation. So basically if we try to write down this matrix, so if we try to write the characteristic equation, basically the expression of the determinant, it will turn out to be and determinant of this form. So for this system to have to basically find out the natural frequencies or basically the eigenvalues of this system, so which will correspond to the natural frequencies of vibration of this system. So we need to basically find out the values of lambda, the roots. So then we have to solve for the roots of this equation, this characteristic equation. So when we basically multiply the determinant, so when we basically do all the algebra to write down the expression of this determinant and then find out the roots of this equation, so basically this will have four roots. because the highest power of lambda is 4. Here in this differential equation it's a uh, fourth power, the highest power of lambda is 4 in this. So then this will have 4 roots which represent, so mostly lambda, the roots will be occurring in either complex, either they will be 4 real values or they will be in complex conjugate pairs. So so then if we try to simplify this differential, this characteristic equation, we will get, like if you do all the after all doing all the algebra of multiplying all these brackets, so we will see an equation of the form lambda to the power 4 plus c1 by m1 plus c1 plus c2 by m2 into lambda to the power 3 plus k1 by m1 plus k1 plus k2 by m2 plus c1 c2 from m1 m2 to lambda square plus k1 c2 plus k2 c1 upon m1 m2 into lambda plus k1 k2 upon m1 m2 is equal to 0. So if we solve for lambda, so basically if we solve this equation for the roots of lambda, so we will get the 4 roots. Let us say we call them as lambda 1 1, lambda 1 2, lambda 2 1 and lambda 2 2, instead of calling them as lambda 1 2 3 4 because they will not be independent. So let us say lambda 1 1 and lambda 1 2 occur as a complex conjugate pair, and lambda 2 1 and lambda 2 2 are another complex conjugate pair. So these are the 4 roots. So then we will get these 4 roots after solving this equation, and we also need to find out, so basically the solution is of the form v e to the power lambda t. So we also need to find out the corresponding vector v corresponding to each root. So we will have z, the total homogeneous equation, homogeneous solution. It will be, so since we will have 4 roots and 4 vectors, let us say, so for lambda 1 1 we will have a corresponding solution like v1 1, then for lambda 1 2 we will have v1 2, lambda 2 1 we will have v2 1, and so on. So we can write the general form of the solution. So we will get v12 corresponding to lambda 12. So we will get basically the general form of the homogeneous uh, so, uh, solution, or basically the free vibrations response. It can be expressed in this form. So the values of C11, C12, C21 and C22, they can be found out from the initial conditions. So basically the initial displacement and initial velocity of the masses, so that can be used to find out uh, the response to the free vibrations. So let us say if we apply an impulse to one of the masses, or give some initial displacement, so then leave the system to oscillate on its own, then based on the initial conditions we can solve for the free vibration problem. The other part uh, of the solution is basically the particular solution. So we will come to that later. So first we will see how to find out the values of v11, v12, v21 and v22. So basically they are like mode shapes corresponding to the eigen values lambda 11, lambda 12, lambda 21 and lambda 22. So we basically write down the characteristic equation here again. Let us say we write it as lambda ij so this into Vij will be 0. So to get the value of Vij, so to find out the relation between the coordinates, like let us say Vij, we will write it as like let us say some v1, v2. So to get the relation between v1 and v2, so we basically try to solve this equation. So we will get, so this will have infinitely many solutions, but there will be a definite relation between the coordinates v1 and v2. So we can write Vij in this form. Let us say plus k1 divided by c1 lambda ij plus k1. So this will be the general form of the eigenvector corresponding to, let us say we call this as an eigenvector corresponding to eigenvalue corresponding to lambda ij. So we will get 4 eigenvalues, so 4 roots here, so 4 eigenvalues, so they will be 4 eigenvectors. So basically we express the general solution for like basically the free vibrations as linear combination of the like in terms of linear combination of the eigenvectors. So this will be basically the free vibration response, and then we continue with the solution, or we basically come to the particular solution. So let us say we have the particular solution of the form ZP of t. So the form of the particular solution will depend on the form of the forcing function. So let us say the forcing function is, let us say, sinusoidal. So then we can assume the form of the particular solution to be of something like this. Let us say, so frequency, let us say it is sinusoidal with frequency omega, let us say. So we can assume a particular solution of the form a1 cos omega t plus a2 sin omega t and b1 cos omega t plus b2 sin omega t and to find out the values of a1, a2, b1, b2, we have to substitute the particular solution in the differential equation. So we will get m into zp double dot plus c into zp dot plus k into zp is equal to the forcing function. So if we solve this differential this equation, we will get a set of two. So if we basically compare the RHS and LHS, to find a1, a2, b1 and b2. We compare the coefficients of the left hand side and right hand side, and based on the coefficients of cos omega t and sin omega t, we will arrive at the values of a1, a2, b1 and b2. So this is how we get the particular solution. And for the free vibrations, we will get the values of C11, C12, C21 and C22 will be can be found out using initial conditions. So that is about solving with basically the free vibrations problem and the forced vibration problem. So this is how we can get the particular solution and the free vibration response. And so generally these equations are difficult to solve using by hand. So we can see that just by adding one more degree of freedom, the algebra becomes fairly complicated. So even the equations, all of these, they become fairly complicated. So just to find out the homogeneous solution and the particular solution, the algebra becomes quite complicated. So we can use a tool like MATLAB to solve some of these problems. So we will see for this kind of a quarter car model, we will see how the example solution, basically we will see how the response of the system changes based on the stiffness and damping characteristics of the system. So for a quarter car model example, so now we will see how to solve these kind of problems using MATLAB. So now let me stop sharing this screen and then let me share my MATLAB window. So now using in MATLAB, so we basically define this quarter car model as a 2 degree of freedom system. So on the right hand side we see basically the representation of the system. So basically this part is the car body, and this is basically the this part represents the wheels, and K1 and C1 basically represent the suspension, and K2 and C2 basically represent the stiffness and damping of the tires. So I have selected some suitable values of the mass, stiffness and damping characteristics which are representative of a particular passenger car. Let us say some so it will be largely, the car body will weigh around 1500 kgs, whereas the combined weight of the wheels will be around 100 kg. The stiffness of the suspension should be about 10,000 newtons per meter, whereas the stiffness of the tire should be around 10 to the power 5 Newton per meter. The damping values are expected to be, they have been selected arbitrarily, uh, but they are expected to be something around that. So we will see how the response of this system looks like when we subject this system. So if we apply these following the initial conditions which are shown over here, y1 of 0 is 0, y2 of 0 is 0, so we don't give any initial displacement. We provide an initial velocity to the lower mass, or basically the tires. Let us say, so the tire is subjected to a small impulse, or so that will impart an initial velocity to the mass m2, and so that will be y2 dot. So that will be, let us say it acquires a initial velocity of 1 meter per second. So the system, so this is how the displacement, velocity and acceleration will look like when it is subjected to this kind of an impulse. So the orange curve, or so the curve corresponding to m2, it will initially show rapid oscillations with high amplitude, and then it will quickly settle down to 0 in about 3-4 seconds or so, whereas the car body is relatively heavier, so that will show sluggish response. It will undergo oscillations of much lower amplitude, but it will take a long time for it the oscillations to settle down, about 20 to 30 seconds. So we see how the response depends on the inertia. So basically the car body has a higher inertia, so because of which the amplitude of oscillations which are felt will be lesser, whereas the tire mass is much lesser, so it will undergo rapid oscillation, but it will quickly settle down to its equilibrium position. So that's how we see the response of the system. So let us look at the, let us say if we animate this particular case. So the lower mass is m2, it will acquire some initial velocity, and then we will see how the response of the system changes as we move ahead in time. So this is the animation of this case. So we can see that the lower mass undergoes oscillations with much higher amplitude, whereas the upper mass, which is the car body, undergoes the oscillations with much lesser amplitude. So basically from this we can see that the suspension is doing its job successfully. We see that it is basically it is not allowing the car body to, it is not transferring much of the vibrations to the car body, so the car body does not move up and down much, whereas the although the tires are actually moving up and down quite significantly. So this is how we would want the suspension to behave ideally. So we saw how the animation of this system looks like. We will just quickly look at the code. So in this MATLAB code we have the initial block, which contains where we give the system data and initial conditions, and we will apply the excitation, basically the either in the form of a force, sinusoidal force, or a sinusoidal displacement. We will try to solve the equation of motion, basically the system dynamics, and so we will basically solve, we will try to get the particular solution. We will derive the eigenvectors, and then the eigenvalues will be determined as roots of the characteristic equation, and we will basically write down the general solution in this block, where we basically find out the unknown constants from the initial conditions. So we basically here in this part we combine the particular solution and the solution to the homogeneous differential equation, and then we plot this response over here in this block. And here we have the code for animation of the motion. So we can basically express the basically we can try to animate whatever the response of this system to whatever initial conditions. So here in this part we can provide the initial conditions, basically the initial displacement and the initial velocities. So here in this example which I have shown over here, I have kept the forcing part of the forcing part to be 0, whereas we have seen the response to a impulse. So if we want to see forced vibration, we can either apply sinusoidal displacement, or we can apply, let us say, some sinusoidal force. Let us say we apply a sinusoidal force of 2000 Newton on this mass, and which is sinusoidal in nature, and if we want to see the response of the system, so this is how the response of the system will look like when it is subjected to sinusoidal forcing. So it initially for few seconds it will there will be some transients because of the free vibration of the system, basically corresponding to the natural frequencies, and then finally the system will acquire the same frequency as that of the forced vibration. So this is like the case where we apply sinusoidal force to the lower mass, or basically the wheels. So we can see that the displacement and velocity are growing in amplitude, and so if we want we can actually extend this simulation for more seconds. So here we can see that like after about 15 to 20 seconds the system will settle down with and vibrate with the oscillations corresponding to the forcing, the sinusoidal forcing. So we can see that the oscillations are at the same frequency as that of the sinusoidal forcing. So this is how you can use MATLAB to solve such kind of problems. So that was all from my end. So with respect to the solving the dynamics of the 2 degree of freedom system. So in today's session we basically saw how we can derive the equation of motion of a 2 degree of freedom system by applying simple Newton's second law. Then we saw how we can express the equation in matrix form, and then try to solve this differential equation for free vibration as well as forced vibrations. So we basically saw with respect to a quarter car model example, where we model the car body and the stiffness and damping characteristics of the suspension, the wheels, its inertia, stiffness and damping characteristics. So in that model we saw how the response of the system can be obtained using MATLAB. So we saw its animation for when an impulse is applied to the wheels, and then we saw how the response can be obtained when it is subjected to some sinusoidally varying force on the wheels. So this was about the solving for the response of a 2 degree of freedom system. So that's all from my side. So any questions? So if not, then we can end the session for today. Thank you for joining. So if there are any questions, you can post. So you can watch the recording of this video and then post your questions in the discussion forum later on. Thank you.